In this tutorial we will use Isaac Lab to train a wheeled quadruped robot to maintain balance on its rear legs. In the beginning of the training, the robot is falling, but after some time, it will learn to stand straight. Isaac Lab is a convenient tool to quickly try well-known machine learning algorithms for your own environment. Let's see how we did this. First, we have to install the Isaac Lab. The installation process is relatively simple. Go to this page. Clone the Isaac Lab repository. Next, install the CMake and Build Essentials packages. CMake is a tool that can build, test, and package software across platforms using simple configuration files. Build Essentials is a meta package that contains a list of packages that are required to create Debian package. To install the Isaac Lab, we just have to execute this command. But before that, we have to make a small modification to the Isaac Lab shell script. Open this script. In the lines 67 and 68, change Python to Python 3. Now execute this script. This script will install all required packages to run Isaac Lab. Depending on the environment, there could be permission issues. In this case, add the sudo command and run this script once again. Now, let's check whether the installation was successful. Open a new terminal in the Isaac Lab directory. Execute the create empty py script. If Isaac Sim window opens, it means that our installation has been successful. Before looking into the code, let's check our problem definition. The objective of the training is to make the robot maintain standing in its upright position. Observations are linear velocity, angular velocity and previous actions. As for actions, the robot can rotate wheels on its rear legs. Also, robot can move its front legs for 45 degrees back and forth from the initial position. A reward is given each step if the robot stands within a specified body angle, that is without falling on the ground. If the robot falls, a penalty is given. Because we want the robot to stand upright as much as possible without leaning back and forth, a penalty proportional to the distance difference between the center of mass from the ground and target height is given each time step. Now we are going to create a USD file of our robot. Please download the wheeled quadruped robot zip file from the Google Drive and extract it to your home directory. We have a Zacro file of our robot under the robot directory. We are going to convert this file into a URDF file. For that, first build this package. Source the setup file. Move to the robot directory. Then, execute the Zacro command. If you have not installed Zacro package, install it using apt. The URDF file will be generated in the same directory as the initial Zacro file. Open the Isaac Sim. From the Isaac Utils tab select Workflows. Then select URDF Importer. Check Merge Fixed Joints option. We use this option to avoid generating unnecessary joints and to keep our model as simple as possible. In the input section, select the URDF file we have previously generated. After the robot model is imported, we have to modify joints property. For joints which will be position controlled, this property is fine. But for joints that will be velocity controlled, we need to change the damping value to 1 and stiffness to 0. This is not the only correct value combination, but stiffness value should be nearly equal to 0 to ensure smooth rotation of joints. Now save this file. The USD file of the quadruped robot will be generated under the quadruped robot directory. Let's look at the code used to launch our environment. Open the create wheeled quadruped envpy file. In these lines, we launch Isaac Lab applications with a specified number of environments. Here, we import Isaac Lab related packages. In this line we specify USD file path of the wheeled quadruped robot. In these lines, property of the rigid body is specified. Here, properties to apply to the root of an articulation are specified. In this part, the initial position of the robot and initial positions of the joints are specified. Note that the initial position of the robot is set so that at the beginning of the episode robot wheels touch the ground. In this part, actuator properties for each joint are specified. As I mentioned previously, properties for position-controlled joints and velocity-controlled joints should be different. To do training, we should specify these 8 settings. These settings will be the same for the most types of problems. Let's see each setting one by one. In the scene configuration, we set ground plane, robot and lights. Lights setting is not essential, but it will make a difference if nice animation is required. In these lines, we set actuation type for each joint. In these lines, we set observation terms. As I mentioned in the problem definition part, we use linear velocity, angular velocity and previous actions of the robot as input for the neural network. Here we specify what happens when an episode ends. In this case, we just reset robot position and all joints position and velocities to default values. Here, reward is set. The robot gets a positive reward when it remains standing for as long as possible. The robot gets a penalty proportional to the difference between center of mass from the ground and target height, and in case the robot falls. There are several default penalty functions defined in the rewards Python script. So, using these functions, it is possible to create basic rewards quickly for your own problem. It is also possible to define custom penalty function. In this part of the code, episode termination condition is specified. The episode ends if a certain amount of time steps passes, or if the robot falls. In this case, if the robot leans more than 60 degrees from its initial position, we treat it as a fall. Again, we can use predefined termination functions or create our own function. Here we can set commands like moving with constant velocity for an asset in the environment, but we will not use this feature in this tutorial. Here we can define curriculum for the learning environment, but we will not use this feature in this tutorial. Now let's execute our code. Run the create wheeled quadruped env Python script. We can see that our environment works properly. Now let's do the training. As a framework, we will use the stable baselines 3. Running training is very simple. Move to this directory. To run training, we just have to execute the train Python script. We can use this code without any modifications. But we have to register our environment, which is referenced as a task in this script. The place where we will put our environment is here. Basically, we have to create the same set of files that we have in predefined environments. Move the wheeled quadruped folder to this directory. In this folder, we have a USD file of our robot. In this folder, parameters for reinforcement learning are stored. In this tutorial we will use this parameter set, but these parameters should be modified depending on the problem. In the init Python script there is a code used to register our environment as gymnasium environment. This environment class is imported from the wheeled quadruped NCFG Python script located in the same directory. Here, name of the environment is specified. The difference between this script and the create wheeled quadruped end Python script is that we don't have an application launching part. The directory in which the USD file located is different. And we don't need the main function since it will be handled by the train Python script. Now, let's run the training. Move to the SB3 directory and execute the training Python script. As a task, specify the environment that we just have created. This time we will run 8 environments. The training process will begin. To run the environment, using a trained model, execute the play Python script. Use last checkpoint option to run latest trained model.